Hi, welcome to the NJC JH Science channel. Hope everyone is doing good. Now, do you know that your weight actually can change in a leaf? Now, actually, it's not really your weight changes because technically your weight remains as a product of mass and gravitational pull by the earth on you. So it shouldn't change. But the reading of your weight from a mass balance will change when you are in an accelerating leaf. And today, we're going to investigate more into this scenario. Now, looking at this question, you are given the weight of a man, 700 newtons. Note how I have already figured out what is the mass of the man by using a simple equation over here. The free body diagram of the man has also been drawn, and there are actually just two forces acting on the man. The trick to solving this question is actually very simple. It's actually to link this scale reading to this value over here. Now, the scale reading given by a mass balance is simply just the same value as the normal contact force acting on the person. And the reason for this will be elaborated later on when we learn about Newton's third law. So, we are going to make this normal contact force our aim for these three parts. Let's tackle the first part. So we will start by applying Newton's second law on the man using the standard way, net force equals to ma. Notice how I have tried to unpack the left hand side, the net force, by using it as a combination of the two forces acting on the man. At right hand side, it just remain it as mass times acceleration. Having downwards as positive, let us now plug in the values very carefully. So n plus a downwards weight of 700 Newton, this still remains as positive, equals to 71.36, and acceleration in part A is given to be 1.8 meter per second square upwards. This means that I must put a negative sign here, negative 1.8 meter per second square. Now, solving this, you should get a value of n to be negative 828 Newton. Alright, so the scale reading actually reads 828 newtons, which is way more than 700 Newton, which is the true weight of the man. Now, in an accelerating leaf, we can sort of get a sensing of why the scale reading is an overestimation of the true weight. If the elevator is accelerating upwards immediately, just imagine a extreme case scenario where the elevator suddenly accelerates upwards. What would you feel? You will feel that you are being pressed downwards towards the floor of the elevator, right? Therefore, you are pressing harder on the scale balance, and hence the scale balance will then give you a slightly higher value. In part B, you have to change the value of acceleration to 1.80 meter per second squared downwards, which is a positive. And if you do this, you will realize that the value of the normal contact force is negative 572 Newton. And this is less than 700 Newton. Now, you can also get the sensing of why in part B, when the elevator is accelerating downwards, the reading of the mass balance would be slightly smaller than the true weight. Imagine an extreme case scenario where the lift suddenly gives way. Would you still be touching the floor? Would the balance still be supporting you as much? The answer is no. Therefore, since we are not pressing down so much on the balance will also give us a slightly smaller value. Part C is the interesting part. If we plug in a value of downwards 9.81 meter per second squared, you will realize that the value of normal contact force will become 0 Newton. Now, do you recall what this means? If the value of normal contact force on the person is 0 Newton, can you see that there's only one force acting on the person, which is the gravitational force, which is the weight? What name do we give to this scenario? Free fall. And in this scenario, if the elevator or the lift is accelerating downwards at 9.81 meter per second square, the lift and therefore whatever that's in the lift will be undergoing free fall. This happens when say the elevator's cable has snapped and the lift safety mechanism didn't kick in, so everything will be free falling, and this is a scenario that you will not want to be in. For more videos like this, do subscribe to our channel. See you next time.